Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 2, Part 2, and we are talking about Section 1, Matter and Atoms. So previously on Part 1, we started the chapter, talked about pure substances, mixtures, physical properties, physical changes, intensive and extensive physical properties, chemical properties, chemical changes, and then we were talking about indications of a chemical reaction. We know that one is a change in temperature, a second is the production of a gas, and then the third is the formation of a precipitate or if the solution turns cloudy. So a precipitate is a solid that comes out of solution. So when we put two solutions together and there's a chemical change, sometimes one of the products is now insoluble. It won't dissolve in the solution, so it's a solid, so it comes out of the solution, and that is the precipitate. And a lot of times in a solution it looks a little bit cloudy. And a fourth indication of a chemical reaction is a change in color. So that's pretty self-explanatory. Something that might get it confused. Oops. All right, I'm back. So a couple of things that could be confused are physical changes where there is a change in color. Food dye, when you add food dye to something, you are just adding color. There's not a chemical reaction. And acid-base indicators, we're not going to get into that too much, but what happens is it's a special chemical that is one color in one formation, and then when there's a hydrogen or it loses a hydrogen, it changes shape, and then it's a different color. So that's actually just changing shape. That's not a chemical reaction. But a lot of times when you see a change in color, it is a chemical change. So let's take a look at page 41. There's a nice picture of our four indicators of a chemical reaction. If it's bubbling and a new gas was formed, if it turns cloudy and a precipitate was formed, if there is a temperature change, often that is a chemical reaction, or if there's a color change, often that is a chemical reaction. So these are all evidence that a chemical change has occurred. When we're talking about chemical changes and atoms and elements and matter, we need to figure out the scale we are talking about. So looking at scales, atoms, and elements, let's talk about macroscopic versus microscopic scales. Let's look on page 42. So things that you can see with your eyes are macroscopic. Sand dunes, a pile of sand, even a single grain of sand. You can see with your eyes. Microscopic is anything that is smaller than that. So anything you would need a microscope with, or anything that's too small you can't even see with a microscope. So when we're talking about atoms and molecules, we are definitely on the microscopic scale. It's almost too small for us to imagine how small they are. So if you take a single grain of sand and cut that up in 200 million pieces, then that would be the size of an atom. And they have a nice illustration here where you have a single grain of sand, and feldspar is a mineral that is often in sand, and then you can see the atoms in feldspar. Coming back to our notes, and again remember you don't have to write what's in purple, but you should write what is in black. So an atom, how big is an atom? It is 10 to the negative 10th meters in diameter. So remember, a millimeter is a thousandth of a meter. So if you were to take a millimeter, which is about the thickness of your fingernail, so a couple sheets of paper, one sheet of paper, probably a couple sheets of paper, and cut that up into about 10 million pieces, then you would get the diameter of an atom. So extremely small. So elements. This is the most fundamental pure substance. Elements make up all matter, and an element is always made up of the same type of atom. So when you have a chunk of gold, all of those atoms are gold atoms. Also, elements cannot be decomposed by chemical changes. So a chunk of gold could go through a chemical reaction, but if you add acid, no matter what you do to it, that gold atom will always be a gold atom. It could be a gold atom in a chunk of gold. It could be a gold atom in a gold solution, but it will always be an atom of gold. So all atoms of the same element have the same structure, and all atoms of that same element are different from atoms of different elements. So again, our gold atoms all have the same structure, they all have the same number of protons, and it is different from an atom of chlorine, which has different numbers of protons and has a different structure. There are 118 elements, and I would like you to come up with at least one element. So there are lots of them. Hydrogen, oxygen, iron, copper, zinc, nickel, phosphorus, gold, silver, einsteinium, sodium, calcium, aluminum, chlorine, boron, helium, neon, argon, nitrogen, sulfur, potassium, lead, bismuth, uranium, carbon, and a whole bunch more. I do want you to write at least 6 of them. You don't have to write all of them down, but write at least 6 elements. Just to be clear, when we're talking about science, water, earth, fire, not elements. These are elements. So the elements are organized into the periodic table. Organizes elements by properties and how they combine with other elements. So this is a super helpful tool, and it will become your friend this year. So let's start off with metals and looking on page 43. Taking a look at our periodic table, we can see the ones in blue are metals, and there are more metals than non-metals. And those are a lot of the elements that we think of as metals, like nickel, copper, aluminum, silver, gold, and even ones that we didn't know, you may not have known were metals, sodium, potassium, calcium, and probably a lot of other elements that you haven't thought about at all before. And then we'll take a look here. We're going to get into the non-metals. So basically everything on the right side, plus this little hydrogen. Hydrogen doesn't always follow the rules, and that'll come up several times on how it doesn't follow the rules. Those are non-metals. We'll talk about those. And then right in the transition period are our metalloids: boron, silicon, germanium, arsenic, and antimony, and we'll talk about those. Metals. The majority of elements are metals. They are on the left side of the periodic table, and one characteristic of metals is that they are good conductors of heat and electricity. So once you have that written down, let's move on to nonmetals. They are going to be on the right-hand side of the periodic table. So metals are all solid with the exception of mercury, whereas nonmetals, they're a little harder to categorize because you can find them in the solid, liquid, or gas phases at room temperature. And they are not good conductors of heat and electricity. Some of them are so bad that they are good insulators. And talking about the organization of the periodic table, each row is called a period, and there are 7 rows. Looking at our 7 rows, 1, 2, 3, 4, 5, 6, 7. These actually go up right here in rows 6 and 7, but we put them down there to save space. And then columns, there are 18 columns. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So columns also have different names. You will hear them referred to as groups and also as families. So those are all words you should learn for column. So let's talk about some things that that are on the periodic table. The atomic symbol is 1, and that one's pretty self-explanatory. It is the symbol for each atom, like hydrogen is H, carbon is C, neon is Ne. So each element gets its own box, and we can see how it's organized. You have your atomic symbol here, and then we have this little number up in the corner is the atomic number. We'll talk about that. And then down here, this decimal, that is the average atomic mass. And then you have your full name. So atomic number, as promised, it is the number of protons, and it is unique to each element. And it's going to increase 1 as you go right down the periodic table. So as you can see, the atomic number, it starts out with 1 with hydrogen, which means hydrogen has 1 proton. Going over here, helium has 2, and then we start in the next row, lithium has 3. And so if you change the number of protons, you get a new element. So average atomic mass and atomic mass unit. So the atomic mass is the mass of an atom. So that's pretty self-explanatory. And it is determined by the number of protons and neutrons. Protons and neutrons are the things in an atom that have mass. So if you have more of them, you have a more massive atom. So please write that down. Atomic mass is the mass of an atom. Mass is determined by a number of protons and neutrons. And atoms are so tiny that kilograms and grams, this is just not going to work for them. So they get their own unit of mass. So atoms are massed in their own unit. And that is creatively named an atomic mass unit, abbreviated AMU. And 1 atomic mass unit is the mass of 1 hydrogen atom, which is 1.66 times 10 to the negative 24th grams. If you could imagine trying to add that with all the exponents, it would be complicated, so it's good that we're going with a simpler unit, AMU. So, for example, 1 carbon atom has a mass of 12.0 AMU. So carbon has 6 protons. All carbon atoms have 6 protons. If they don't, they're not carbon. And then a lot of them have 6 neutrons, so 6 and 6 is 12, and that is its mass. However, I did say that not all carbons have 6 protons and 6 neutrons. They all have 6 protons, but they don't have to have 6 neutrons. They can still be a carbon if you have 7 or 8 neutrons. So we have to take the average atomic mass of all the carbon atoms in the world, and that is 12.011 AMU. So almost all of them are carbon 12, but there's a couple of carbon 13 and a couple of carbon 14 in there. So the average atomic mass is 12.011 AMU. And the average atomic mass for all of the elements is found on the periodic table. And this number is going to be really helpful throughout the year, so let's take a look at that. So for example, lithium has an average atomic mass of 6.941 atomic mass units, and we know that carbon has an atomic mass of an average atomic mass of 12.011 AMUs. Hydrogen has an average atomic mass of 1.0079 AMUs, and I think you get the point. We're going to pause there, and then in our next video we're going to tackle moles, which is a very important concept. Perhaps you've already done a mole day coloring page in previous years, and this will be a constant chemistry friend concept that you should know. So I will see you then. Bye.